Good morning, my friend. Today we share knowledge about the heat plant block diagram, thermal power, coal-fired power plant, the scope, the thermodynamic principle governing steam generator and energy conversion, detailed analysis of the system component including boiler, turbine, condenser, feed water heater, and generator. Performance metric across various operation conditions, 50%, 75 TMCR, and VWO. Efficiency improve strategy target, feed water heating, turbine performance, and connection operator. Objective: technical use precise engineering terminology and standard. Analysis: evaluate system performance using thermodynamic data. Instructional design to education and inform professional and trainee. System following the logic flow for the component definition and performance analysis. Practical over untenable recommendation for the improvement plant efficiency. This heat balance diagram on the you can see. So once we see this, we try to understand what we can see is, so the flow or G, this one, mass flow rate of the steam and water kilogram per hour, pressure or P, steam or water pressure megapascal, temperature or T, thermal condition degree C, enthalpy or H, total heat content per unit mass, kilogram per joule. If we want to understand where is the water is after condenser, before heat water, steam superheater, after boiler to turbine inlet, and saturated steam in heater or low pressure turbine stage, and condenser cover exhaust steam to water by removing head. If you see this have 6 stages, number 1, number 2, generator, number 4, number 5, number 6. Number 6 and number 5 is LP, number 4, number 2, and number 1 is LP, HP, high pressure heater, then this one is generator. If see the water temperature is for the number C is 42 degrees C and 177 enthalpy, kilojoule per kilogram. We go to the stage number 5, 68.7 degrees C, 288 kilojoule per kilogram. And we go to the number 4 is the 102 degrees C and 428 enthalpy. And we go to the number 2 is 159 degrees C and 681 enthalpy. And we go to number 1, this is the higher one, the last one, 181 degrees C and 773 kilojoule per kilocalorie enthalpy. Based on this heater, then the water will supply to the boiler. Then from the boiler will supply superheater steam by 8.83 megapascal by 535 kilojoule degree C and 3,476 kilojoule per kilogram enthalpy. If you can see this from the number 6, 177 enthalpy, then become 3,476 is enthalpy. So then, based on this energy, will turn turbine, then turbine will transfer the energy to the electric generator. So this condition is based on the 50% TMCR for the load 3000 kilowatt. Then heat rate is 9722 kilojoule per kilowatt hours and throttle flow 11,000 and 700 kilogram per hour. So the fluid flow is clockwise. They will coming from just this scenario. They will coming from the feed water coming to the number 6, STR number 6, number 5, number 4, number 2, number 1, go to boiler, go the turbine, then will come back to become condenser and come back to the water. So this will circulation to understand how the flow of the fluid for the power plant. I will give another example. This heat balance diagram based on the condition 75 TMCR. So the number 60 HTL, number 5 HTL, number 4 HTL, number 2 HTL, and number 1 HTL. Then if you see, then very much different is on the enthalpy, the steam before go entering to the turbine, the 34,476 kilojoule per kilogram enthalpy. So if you want to understand more detail, HTL number 1, number 2, number 3, and number 5 and number 6, and generator, along with the key, different and impact on the plant efficiency. Generator, remove dissolved gas O2, CO2 from the feed water and mix condensate with the heat rate. Temperature and enthalpy not explicit labeling in this image, but typically around 105 until 120 degrees C and 550 kilojoule per kilogram. The key difference among HTR temperature and LTP condition. Number 1, the highest temperature and enthalpy indicating this position is close to the boiler. STR number 6 is the lowest and showing is earlier in the heating sequence. Steam extraction source and HTR number 1 receives steam from the high pressure turbine stage. Okay, this one turbine. So coming from this one turbine, go to heater. We go to number 5 and number 6. Receive steam from intermediate and low pressure state feed watering heating sequence. So you see this diagram. Through feed water flow, through number 6, number 5, number 2, number 1, before entering the boiler. Impact of all HTR on the plant efficiency, number 1, 2, 3, 4, 5, 6. Preheat feed water reduce the energy required in the boiler. The lower fuel consumption. This why, as my understanding, this temperature is very important. Cycle efficiency, higher feed water temperature improve Rankine cycle efficiency. Heat rate reduce, effective TS operator lower and heat rate, kilojoule per kilogram, meaning less energy is needed per unit of electric. Environment benefit, reduce fuel using lead to the lower emission and operational cost. So the logic understanding, when the water entering to the boiler are the high, so the boiler is no need much energy to increase temperature up to the turbine requirement. Okay, I give you another example, the condition TMCR. Turbine maximum continuously running operating metric load is 6,000. Represents the electric output of the turbine under the full load condition. Heat rate 8,994 kilojoule per kilowatt hours indicate amount with this heat energy required to generate unit kilowatt per hours of electricity. Lower value reflect to better thermal efficiency. The steam rate 3,672 kg per kilowatt hours measure the mass of the steam consumed per unit electricity produced is the lower steam rate mean efficiency time utilized. Throttle flow 220 390 kg per hour total mass flow rate is steam entering the turbine. This one. Reflect to the volume of steam required to the sustain TMCR output. Efficiency inside the this value represent of design performance of the plant full load and combined of the moderate heat rate and low steam indicate as well as optimum steam cycle. Maintaining this parameter ensure the fuel efficiency cost effective and environmentally respond power generation. Okay, I give you another example. VWO, valve wide open. Valve WO refer to turbine operated with the control valve full open. Use performance testing on overload condition may exceed the TMCR slightly in load and steam flow. Example, 62,000 kilowatt load. Okay, 232 kilogram per kilogram hours steam flow. So you can see the enthalpy is 3,476, but they can give load is 62,900 kilowatt. So what you can show in his balance diagram, energy input from the fuel represent the heat added in the boiler, fuel consumption, general thermal energy to convert water into the high pressure steam. Heat at boiler, the steam is generated at high pressure temperature. Example, 8.83 MPa, 535 degrees C, enthalpy increase significant up to 3,476.6 kilojoule per kilocalorie. This is starting point to steam cycle. Work output from the turbine. Steam expand through the turbine stage, produce mechanical work, and this work drive to generate and produce electricity, and temperature drop as the energy and extraction. Heat rejection in condenser. Exhaust steam from the turbine is condensed back to the water. Heat rejected the cooling tower and river, maybe seawater. This step is completely the Rankine cycle. So this is very basic formula. I think you are also very familiar with this Rankine cycle. Flow of the water and steam. The diagram show steam flow from the boiler to the turbine, extraction steam from feed water heater, condenser flow from the condenser to the aerator, feed water flow back to the boiler by pump and heater. So major equipment contribution here is boiler and steam generator, condenser, feed water, control valve and throttle valve, and you also understand about the SSR, steam seal regulator, maintain sealing steam pressure in the turbine gland. Based on the, for example, heat balance diagram, still we can improve? Yes, of course. Improvement 1, optimize feed water heating and performance. The location is STR number 1 to number 6 between condenser and feed water pump. Action clean heat exchanger surface, calibration control valve, reduce terminal temperature difference, upgrade instrumentation for temperature monitoring, impact high feed water temperature. Is mean the water entering starting with the good temperature, reduce boiler feed demand, improve heat rate and steam rate. Improvement 2, upgrade turbine efficiency on the HP, IP, LP and stage. Location is main steam turbine. Action, reblade turbine state, improve gland sealing system, reverse base diagram and nozzle, install connection and monitoring. But this section, you need to, maybe requirement is, you need to consult the turbine manufacturing. Impact more mechanical work from the steam, increase power output, better energy conversion. Improvement 3, improve condenser and the cooling system performance. The location is on the condenser after low pressure turbine exhaust. Action, clean condenser tube, optimize cooling water flow, maintain vacuum and system, upgrade cooling tower and fans. So this is when you do is maintenance, cleaning, greasing and tightening. Then you can see this one, and the clean turbine condenser is for the specialist one is not so difficult work, but you must under training and monitoring by experienced people. The impact, low turbine exhaust pressure, increase expansion efficiency, improve cycle efficiency. So this is the reference. Maybe the new code you see is ASME PTC steam turbine. Once you need to count the power plant efficiency, also you need to understand this ASME PTC. Conclusion. Technically, detailed overview of the heat balance and performance characteristic of coal-fired thermal power plant through the analysis thermodynamic, parameter, component, and function and product condition, including 50%, 75%, TMCR, and VWO. Heat balance diagram effectively illustrate the flow of the energy working fluid through the Rankine cycle. Highlight the role of the steam generation, expansion, condensation, feed water recovery. Component integration, coordinate operator of the boiler, turbine, condenser, feed water heater, HCR, and generator is essential for maintaining thermal efficiency of operational stability. Performance metric, key indicators such as heat rate, steam turbine, throttle flow profile, quantifiable measurement of system efficiency, TMCR condition, serve and design benchmark for optimum performance. Efficiency optimizing, improve in the feed water heating, turbine efficiency, and condenser performance directly contribute to reduce the fuel consumption, lower emission, and heating cycle efficiency. Knowledge and application. This content is meant to support the technical decision making, operating training, maybe performance improve initiative within the power generation facility. This is my end presentation. I hope can use for you. Thank you and goodbye.